All right, let's talk about Gauss's law. So Gauss's law is a really, really powerful tool, and I think that it is deceptively easy. Like, people think it's going to be hard, but it turns out it's actually really easy. It's also a good thing for you guys to review, because when I was doing the training on Physics C, um, I guess 2 summers ago, the instructor told us that oftentimes understanding Gauss's law is what separates the 4 students from the 5 students. So I think this is going to be a important topic for you guys to review. But let's start with the basics. You have a point charge. There it is. Ta-da. It has a charge of plus Q. So it has an electric field that looks, let's make it a little bit bigger, kind of like this. And it points outwards because it's positive. So what we can do is we can say, let's draw a Gaussian surface around our point, and we're going to add up all the electric field that passes through. So I like to call it magic circle, magic sphere, or magic sphere, depending on my mood. So we're going to draw that as a dashed line and say how many electric field lines pass through here, how much electric field passes through. Now, it also, you can note, it doesn't matter how big I draw my sphere, I still have the same number of electric field lines passing through when I add up in total. Sure, it's weaker because they're farther apart out here and you're farther from the charge, but if I add up the total, it's still the same. All right, so what does Gauss's law tell us? Well, Gauss's law tells us that we can do stuff with electric flux if we want to. I don't think it's particularly important, but I'll do it just because AP sometimes likes to ask about flux. But really, flux is kind of a meaningless concept outside of Gauss's law and outside of like the rate of its change. Like, flux on its own doesn't really do anything. So they say the electric flux is constant. So the electric flux is equal to the dot product of the electric field and the area. Or if you want to be real accurate, what we could actually do is say the flux is equal to the path integral, or the surface integral, I guess, of the electric field dot product with the differential of the area element, so the infinitesimal area element. But really, since we're doing a sphere here, we can use this one, and we can even just say that the surface area of a sphere, right? We all know the surface area of a sphere should be 4 pi r squared, right? So in this case, my flux is going to be electric field times 4 pi r squared. But so what do we do with flux? Well, the other thing we know about flux is we know that the flux is equal to the charge enclosed inside a sphere divided by the permittivity of free space. Now, if this weren't free space, we'd just erase the knot there and throw it, and we could do, or we could throw in the dielectric constant out front, and that would be fine. It wouldn't be much different, but we're just going to do free space for now. So this is the charge enclosed. That's important. So it's not just the total charge. If I leave some charge out of my Gaussian surface, then it doesn't count towards this. Okay. So now in the end, what we have is that the electric field times the area is equal to the charge enclosed divided by epsilon naught, right? So let's go ahead and plug things in. So if we're looking at a sphere of radius r, y, z, I don't care what you call it, d, it's going to be basically the same. So it's going to be electric field times 4 pi r squared. I'll put that in parentheses just so you can see I substituted in, times the charge enclosed, which is plus q, over epsilon naught. So now all I'm doing is solving for the electric field, right? So E then is equal to Q over epsilon naught times 4 pi r squared. And then, just for the sake of putting it in the right form, because normally there's a certain way you see this, let's go ahead and just rearrange this so all the constants are together and my variables are not. are separate. So we're going to slide this up a hair. So your electric field then is equal to Q over 4 pi epsilon naught times 1 over r squared. Or some people like to put the Q on this side. Doesn't really matter to me. Depends on if you're considering a variable or not. So that's the very basics of Gauss's law. So, and one thing that's important to know is if I had said that we had done a sphere instead, like this, a charged sphere of plus q, right? If I put a Gaussian surface around this thing, it's still going to act just like a point charge, right? You're still going to get the same thing. We'll still have, say, my electric field times the area of my Gaussian surface, which is still 4 pi r squared, is equal to charge enclosed over epsilon naught. So electric field times 4 pi r squared is equal to q over epsilon naught. And you can see it's going to go the exact same way because it's the exact same formula. Yeah, that's it for the basics of Gauss's law. I'll pick up here for the next video, guys.